Hello, and welcome to Discover Advancements in iOS Camera Capture. I'm Nicholas Gello from the Camera Software team, and I'll be presenting some exciting new features in iOS and iPadOS. I'll begin with how to stream depth from LiDAR scanners using AV Foundation. Next, I'll look at how your app will receive improved face rendering with face-driven autofocus and autoexposure. Then, I'll take you through advanced AV Capture session streaming configurations. And lastly, I'll show you how your app will be able to use the camera while multitasking. I'll begin with how to stream depth from LiDAR scanners using AV Foundation. The iPhone 12 Pro, iPhone 13 Pro, and iPad Pro are equipped with LiDAR scanners capable of outputting dense depth maps. The LiDAR scanner works by shooting light onto the surroundings and then collecting the light reflected off of the surfaces in the scene. The depth is estimated by measuring the time it took for the light to go from the LiDAR to the environment and reflect back to the scanner. This entire process runs millions of times every second. I'll show you the LiDAR scanner in action using AV Foundation. Here, on an iPhone 13 Pro Max, I'm running an app that uses the new LiDAR depth camera AV capture device. The app renders streaming depth data on top of the live camera feed. Blue is shown for objects that are close, and red for objects that are further away. And using this slider, I can adjust the opacity of the depth. This app also takes photos with high-resolution depth maps. When I take a photo, the same depth overlay is applied, but with an even greater resolution for the still. This app has one more trick up its sleeve. When I press the torch button, the app uses the high-resolution depth map with the color image to render a spotlight on the scene using RealityKit. I can tap around and point the spotlight at different objects in the scene. Look at how the spotlight highlights the guitar. Or if I tap on the right spot of the corner of the wall, the spotlight forms the shape of a heart. Let's go back to that guitar. It looks so cool. API for the LiDAR scanner was first introduced in ARKit in iPadOS 13.4. If you haven't seen the WWDC22 presentation, Explore ARKit 4, I encourage you to watch it. New in iOS 15.4, your app can access the LiDAR scanner with AV Foundation. We've introduced a new AV capture device type, the built-in LiDAR depth camera, which delivers video and depth. It produces high-quality, high-accuracy depth information. This new AV capture device uses the rear-facing wide-angle camera to deliver video with the LiDAR scanner to capture depth. Both the video and depth are captured in the wide-angle camera's field of view. And like the TrueDepth AV capture device, all of its formats support depth data delivery. This new AV capture device produces high-quality depth data by fusing sparse output from the LiDAR scanner with the color image from the rear-facing wide-angle camera. The LiDAR and color inputs are processed using a machine learning model that outputs a dense depth map. Because the LiDAR depth camera uses the rear-facing wide-angle camera, the telephoto and ultra-wide cameras can be used in addition with an AV capture multicam session. This is useful for apps that wish to use multiple cameras at the same time. The LiDAR depth camera exposes many formats, from video resolutions of 640 by 480 to a full 12 megapixel image at 4032 by 3024. While streaming, it can output depth maps up to 320 by 240. And for photo capture, you can receive depth maps of 768 by 576. Note, the depth resolutions are slightly different for 16 by 9 and 4 by 3 formats. This is to match the video's aspect ratio. The LiDAR depth camera AV capture device is available on iPhone 12 Pro, iPhone 13 Pro, and iPad Pro 5th generation. iPhone 13 Pro can deliver depth data using a combination of the rear-facing cameras. The AV Foundation Capture API refers to these as virtual devices that consist of physical devices. On the back of the iPhone 13 Pro, there are 4 virtual AV capture devices available to use. The new LiDAR depth camera uses the LiDAR scanner with the wide-angle camera. The dual camera uses the wide and telephoto cameras. The dual wide camera, which uses the wide and ultra-wide cameras. And the triple camera that uses the wide, ultra-wide, and telephoto cameras. There are differences in the type of depth these devices produce. The LiDAR depth camera produces absolute depth. The time-of-flight technique used allows for real-world scale to be calculated. For example, this is great for computer vision tasks like measuring. The TrueDepth, dual, dual-wide, and triple cameras produce relative disparity-based depth. This uses less power and is great for apps that render photo effects. AV Foundation represents depth using the AV Depth Data class. This class has a pixel buffer containing the depth with other properties describing it, including the depth data type, the accuracy, and whether it is filtered. It is delivered by a depth-capable AV capture device, like the new LiDAR depth camera. You can stream depth from an AV capture depth data output, or receive depth attached to photos from an AV capture photo output. Depth data is filtered by default. Filtering reduces noise and fills in missing values or holes in the depth map. This is great for video and photography apps, so artifacts don't appear when using the depth map to apply effects on a color image. However, computer vision apps should prefer non-filtered depth data to preserve the original values in the depth map. When filtering is disabled, the LiDAR depth camera excludes low confidence points. To disable depth data filtering, set the Is Filtering Enabled property on your AV capture depth data output to false. And when you receive an AV depth data object from your delegate callback, it will not be filtered. Since ARKit already provided access to the LiDAR scanner, you might ask, how does AV Foundation compare? AV Foundation is designed for video and photography apps. With AV Foundation, you can embed depth data captured with the LiDAR scanner into high-resolution photos. ARKit is best suited for augmented reality apps, as the name suggests. With the LiDAR scanner, ARKit is capable of delivering features like scene geometry and object placement. AV Foundation can deliver high-resolution video that is great for recording movies and taking photos. AV Foundation's LiDAR depth camera can output depth up to 768 by 576. This is more than twice as big as ARKit's depth resolution of 256 by 192. ARKit uses lower resolution depth maps so it can apply augmented reality algorithms for its features. For more in-depth information on how to use AV Foundation to capture depth data, watch our previous session, Capturing Depth in iPhone Photography from WWDC 2017. We're excited to see the interesting ways you can use the LiDAR depth camera in your apps. Next up, I'll discuss how improvements to the autofocus and autoexposure systems help to improve the visibility of faces in the scene for your app. The autofocus and autoexposure systems analyze the scene to capture the best image. The autofocus system adjusts the lens to keep the subject in focus, and the autoexposure system balances the brightest and darkest regions of a scene to keep the subject visible. However, sometimes the automatic adjustments made do not keep your subject's face in focus. In other times, the subject's face can be difficult to see with bright, backlit scenes. A common feature of DSLRs and other pro cameras is to track faces in the scene to dynamically adjust the focus and exposure to keep them visible. New, in iOS 15.4, the focus and exposure systems will prioritize faces. We like the benefits of this so much that we've enabled it by default for all apps linked on iOS 15.4 or later. I'll show you some examples. Without face-driven autofocus, the camera stays focused on the background without refocusing on the face. Watch it again. Look at how his face remains out of focus as he turns around, and that the trees in the background stay sharp. With face-driven autofocus enabled, you can clearly see his face. And when he turns away, the camera changes its focus to the background. When we compare the videos side by side, the difference is clear. On the right, with face-driven autofocus enabled, you can see the finer details in his beard. With bright backlit scenes, it can be challenging to keep faces well exposed. But with the auto exposure system prioritizing faces, we can easily see them. Comparing side by side, we can see the difference here again. Notice that by keeping his face well exposed in the picture on the right, the trees in the background appear brighter. And the sky does too. The exposure of the whole scene is adjusted when prioritizing faces. In iOS 15.4, there are new properties on AV Capture device to control when face-driven autofocus and autoexposure are enabled. You can control whether the device will automatically adjust these settings, and decide when it should be enabled. Before toggling the enabled properties, you must first disable the automatic adjustment. The automatic enablement of this behavior is great for photography apps. It's used by Apple's camera app. It's also great for video conferencing apps to keep faces visible during calls. FaceTime takes advantage of this. But sometimes, it's not best suited for an app to have the autofocus and autoexposure systems be driven by faces. For example, if you want your app to give the user manual control over the captured image, you might consider turning this off. If you decide face-driven autofocus or autoexposure is not right for your app, you can opt out of this behavior. First, lock the AV Capture device for configuration. Then, turn off the automatic adjustment of face-driven autofocus or autoexposure. Next, disable face-driven autofocus or autoexposure. And lastly, unlock the device for configuration. I'll talk about how you can use advanced streaming configurations to receive audio and video data that is tailored for your app's needs. The AV Foundation Capture API allows developers to build immersive apps using the camera. The AV Capture session manages data flow from inputs, like cameras and microphones, that are connected to AV Capture outputs that can deliver video, audio, photos, and more. Let's take a common camera app use case for example, applying custom effects like filters or overlays to recorded video. An app like this would have an AV Capture session with two inputs, a camera and a mic, that are connected to two outputs, one for video data and one for audio data. The video data then has the effects applied, and the processed video sent two places, to the video preview and an AV Asset Writer for recording. The audio data is also sent to the AV Asset Writer. New in iOS 16 and iPadOS 16, apps can use multiple AV Capture video data outputs at the same time. For each video data output, you can customize the resolution, stabilization, orientation, and pixel format. Let's go back to the example camera app. There are competing capture requirements this app is balancing. The app wants to show a live video preview of the content being captured and record high-quality video for later playback. For preview, the resolution needs to be just big enough for the device's screen, and the processing needs to be fast enough for low latency preview. But when recording, it's best to capture in high resolution with quality effects applied. With the ability to add a second AV Capture video data output, the capture graph can be extended. Now, the video data outputs can be optimized. One output can deliver smaller buffers for preview, and the other can provide full-size 4K buffers for recording. Also, the app could render a simpler, more performant version of the effect on smaller preview buffers, and reserve high-quality effects for full-size buffers when recording. Now, the app no longer has to compromise its preview or recorded videos. Another reason to use separate video data outputs for preview and recording is to apply different stabilization modes. Video stabilization introduces additional latency to the video capture pipeline. For preview, latency is not desirable as a noticeable delay makes it hard to capture content. For recording, stabilization can be applied for a better experience when watching the video later. So, you can have no stabilization applied on one video data output for low latency preview, and apply stabilization to the other for later playback. There are many ways to configure the resolution of your video data output. For full-size output, first, disable automatic configuration of output buffer dimensions. Then, disable delivery of preview-sized output buffers. In most cases, however, the video data output is already configured for full-size output. For preview-sized output, again, disable the automatic configuration, but instead, enable delivery of preview-sized output buffers. This is enabled by default when using the Photo AV Capture Session preset. To request a custom resolution, specify the width and height in the output's video settings dictionary. The aspect ratio of the width and height must match the aspect ratio of the source device's active format. There are more ways to configure your video data output. To apply stabilization, set the preferred stabilization to a mode like Cinematic Extended, which produces videos that are great to watch. You can change the orientation to receive buffers that are portrait. And you can specify the pixel format to receive 10-bit lossless YUV buffers. For more information on selecting pixel formats for an AV Capture video data output, see TechNote 3121. In addition to using multiple video data outputs, starting in iOS 16 and iPadOS 16, apps can record with AV Capture movie file output while receiving data from AV Capture video data output and AV Capture audio data output. To determine what can be added to a session, you can check whether an output can be added to it and query the session's hardware cost property to determine whether the system can support your configuration. By receiving video data with the movie file output, you can inspect the video while recording and analyze the scene. And receiving audio data with the movie file output, you can sample audio while recording and listen to what is being recorded. With a capture graph like this, you can offload the mechanics of recording to AV Capture movie file output while still receiving uncompressed video and audio samples. Implementing these advanced streaming configurations requires use of no new API. We have enabled this by allowing you to do more with existing API. And lastly, I'll discuss how your app will be able to use the camera while the user is multitasking. On iPad, users can multitask in many ways. For example, recording voice memos while reading notes in split view. Or with slide over, write notes in a floating window above Safari in full screen. With picture-in-picture, you can continue video playback while adding reminders to watch more WWDC videos. And with Stage Manager new to iPadOS 16, users can open multiple apps in resizable floating windows. Starting in iOS 16, AV capture sessions will be able to use the camera while multitasking. We prevented camera access while multitasking before because of concerns of the quality of service the camera system can deliver while multitasking. Resource-intensive apps like games running alongside an app using the camera can induce frame drops and other latency, resulting in a poor camera feed. A user watching a video months or years later that has poor quality may not remember that they recorded it while multitasking. Providing a good camera experience is our priority. When the system detects video from the camera was recorded while multitasking, a dialog will be displayed informing the user about the potential for lower quality videos. This dialog will be presented after recording has finished with AV Capture movie file output or AV Asset Writer. It will be shown only once by the system for all apps and will have an OK button to dismiss. There are two new properties added to AV Capture Session to indicate when multitasking camera access is supported and enabled. Capture sessions that have this enabled will no longer be interrupted with the reason video device not available with multiple foreground apps. Some apps may wish to require a full screen experience to use the camera. This may be useful if you wish for your app to not compete with other foreground apps for system resources. For example, ARKit does not support using the camera while multitasking. You should ensure your app performs well when running alongside other apps. Make your app resilient to increasing system pressure by monitoring for its notifications, and take action to reduce the impact, like lowering the frame rate. You can reduce your app's footprint on the system by requesting low resolution, bin, or non-HDR formats. For more information on best practices of maintaining performance, read the article Accessing the Camera While Multitasking. Also, video calling and video conferencing apps can display remote participants in a system-provided picture-in-picture window. Now your app's users can seamlessly continue a video call while multitasking on iPad. AVKit introduced API in iOS 15 for apps to designate a view controller for displaying remote call participants in. The video call view controller allows you to customize the content of the window. To learn more about adoption, please see the Adopting Picture-in-Picture for Video Calls article. And this concludes advancements in iOS camera capture. I showed how you can stream depth from LiDAR scanners using AV Foundation, how your app will receive improved face rendering, advanced AV Capture Session streaming configurations tailored for your app, and lastly, how your app can use the camera while multitasking. I hope your WWDC rocks.